Hello, good morning. This is a new colloquium from the Instituto de Astrofísica de Andalucía, from the Severo Ochoa program. And today we will have the talk by Dr. Rubén López-Coto, and he will talk about the tera-electron bolts halos and their connection to the leptonic cosmic flux measured at the Earth. Rubén will be introduced by Isabel Marquez, our scientific director. Isabel?
Hello, good morning, everybody. Thank you very much for coming here again for another weblogium from the Severo Ochoa program at the IAA. It's a pleasure for us to have Rubén López-Coto that I'd like to thank first for accepting our invitation to be, in fact, in person at the IAA. So it's a pleasure for us to have you here, Rubén. And I just remind people at the IAA that Rubén got already in 2009 a high intro fellowship here at the IAA, and then he followed a period between 2010 and 11. Rubén López-Coto obtained his PhD in physics in 2015 in the Universidad Autónoma de Barcelona, with a thesis entitled Very High Energy Observations of Pulsar with Nebulae and Cataclysmic Variable Stars with Magic, as well as development of trigger systems for Imaging Atmospheric Cherenkov Telescopes. His thesis was awarded with the Extraordinary Doctorate Award by the Universidad Autónoma de Barcelona, and also with the Springer Thesis Award that resulted in a publication as a book with Springer. So great success. Then he got a 2-year postdoc position at the Max Planck Institute for Kern Physics in Heidelberg, Germany, where he was involved in the analysis of galactic sources with HAWC telescope and with HAWC, and on the upgrade of the HAWC observatory. In 2017, he obtained the Italian National Postdoctoral Fellowship in Experimental Physics and moved to the astrophysics group of the Istituto Nazionale di Fisica Nucleare in Padova, where he continued his research in the field of very energetic, high energy cosmic and gamma rays within MAGIC, HAWC, and CTA collaborations. Since 2019, he develops his work at the Istituto Nazionale di Fisica Nucleare in Padova with an European Marie Skłodowska-Curie Fellini Fellowship. He has been first or corresponding author in papers in physical review letters in Science and in Nature Astronomy, for instance. He has also teaching activities as well as supervising of master's and PhD thesis. And he's currently the coordinator of the Galactic Working Group of the MAGIC collaboration, the software co-coordinator of the large-sized telescope, the LST, CTA. He's member of executive board of the LST, and he's the Galactic coordinator of the SWGO and coordinator of Deep Learning Working Group of MAGIC. Today, as you know, he talked about the tera-electron bolts halos and the connection to the Leptonic Cosmic Ray flux measurements at the Earth. Thank you very much again, Rubén, for being here, and the board is yours.
Thank you very much, Isabel, for the nice introduction. Well, I first need to start thanking, first of all, the IAA for allowing me to be here, and also of course, the Severo Ochoa program for inviting me here to IAA to be able to give this talk and also to spend here 6 months. So thank you very much to all of you. And yeah, I hope that you see my screen, full screen. So today I'm going to talk to you about TeV Halos and their connection to the leptonic flux measured at the Earth. So here you have an outline of my talk. And well, I will start giving you a few words about cosmic rays. So even though you may know most of what I'm gonna say, this will help me to put in context the measurements that we've been performing and why are they so important. Then I will start talking about the sources that we have studied and their connection to these cosmic ray fluxes that we measured here at the Earth. And finally, I will describe what is let's say the products that these sources produce here in the measurements that we perform of cosmic ray fluxes, direct measurements here at the Earth. So let me start giving you a few words about cosmic rays and about the spectrum composition. So cosmic rays are usually considered only the charged particles, ultra-relativistic charged particles that extend for over 12 decades in energy, as you can see over there in the plot that is on the left, and that have a different origin depending on their energies. So the low energy ones, the one below 1 gigaelectron volt, they have a solar origin. The one between 1 GeV and around 1 PeV, they are thought to be of galactic origin. And the ones above beta electron volt energies, they necessarily need to be of extragalactic origin. So most of these cosmic rays, they are protons and helium nuclei, but we have also other species like heavier nuclei. And the most important ones, or one of the most important ones in order to understand their propagation, especially nearby the Earth, are electrons and positrons, because how fast they lose their energy. So I will now describe electrons and positrons. As you know, these are the leptons, or the leptonic fluxes that we measure here at the Earth, that are in the title of this talk. So positrons and electrons in the cosmic rays. So basically over here in this plot, this is quite an old one, but it is very handy in order to make the point that I'm just gonna make. And you can see that basically we have some kind of primary cosmic rays and secondary cosmic rays. So primary cosmic rays, they are accelerated at the sources. And for example, electrons, they are thought to be accelerated in primary in supernova remnants. So that would be the curve that you can see here at the top. Then you have also cosmic rays of secondary origin. The cosmic rays of secondary origin are those that are produced in cosmic ray collisions with particles of the interstellar medium. For example, a proton, we have many protons in the cosmic rays, hits a particle in the interstellar medium and produces a positron. And those are the ones that you can see here. In this second line. So you also have secondary electrons, but they are less abundant. And basically, if we assume that all the positrons are of secondary origin and all the electrons are of, well, most of the electrons are of primary origin, if you take the ratio of this curve of the curve of the positrons over the curve of the electrons, then you get something that should be decreasing with energy. And this is what is called the positron fraction. And in principle, this fraction that is simply the ratio between the two curves that I showed you before, because of how the spectra of these secondary positrons and these primary electrons are, in principle, that should be decreasing with energy. But this is actually only the case for energies below a few GeV. And it was already some 10 years ago already that Pamela and later AMS measured that this is actually not the case when you go for energies above a few GeV. And basically over there in the shaded area is what you would expect from secondary production, but the measurements already show that there is actually another contribution that makes the positron fraction to go up. So what is the origin of these new positrons? So these new positrons, since they cannot come from secondary sources, they should be coming from, from not sources, but from secondary origin. They should be coming from sources. And what are these sources? So the most popular ones is to assume that this comes from dark matter, but well, this assumption has some tensions with the latest measurements and so on. And the most, let's say, the most popular mundane source is actually that these positrons are actually generated by pulsars, and by pulsars, and not only pulsars, but also their associated nebulae. So let me now give a brief description of what are the pulsar these pulsar nebulae, in which these electrons and positrons that we know that are generated in the pulsar's magnetospheres, well, how they are accelerated and how they can actually escape and reach us here to the Earth, and whether they could be significant contributors of this positron flux. So, well, first of all, here you have a cartoon with the evolution of pulsar nebulae. So basically, we have a supernova explosion that leaves us a remnant neutron star that rotates very fast and creates this wind of electrons and positrons that escape from this pulsar magnetosphere. When the neutron star is very young, you still have all the supernova remnant material, and basically everything that you get is pretty symmetric. So all this electron and positron wind, it finds the supernova remnant, it is compressed by it, and it doesn't allow it to grow very much, let's say. And well, you have something that is very bright in radio, X-rays, also very high energy gamma rays, but it is basically symmetric. Then when you go to later stages, when you go to ages between, I don't know, tens of kiloyears up to hundreds of kiloyears or so, then you already have the supernova remnant reverse shock that compresses the pulsar nebula. Also, the pulsar has a proper motion that it starts to become significant, in the sense that the electrons and positrons that it is injecting into this supernova remnant pulsar nebula complex, they are being injected from a different region than the one where the pulsar was born, and this is creating a source that is much more irregular. It is actually very bright in very high energy gamma rays, because the magnetic field starts to decrease and we have more inverse compton rather than synchrotron. And then what happens when we go to a later stage, to a stage when we have a pulsar that is older than 100 kiloyears. So this relic stage, that it was called like this in the past, it is actually not. It was actually never measured that we would get a pulsar that was escaping from the parent supernova, and we did not really know what was going to happen. So what was postulated was that this pulsar could produce a nebula, a small synchrotron nebula of all these electrons and positrons that are being injected. The pulsar is not powerful anymore, so it was difficult to say whether you were going to detect that or not. And what was happening to those electrons and positrons afterwards, it was a mystery. Here in this slide, I put you a couple of examples of a young middle-aged pulsar nebulae, and as I said, in this relic stage, this all pulsar nebulae, well, or all pulsars, we didn't really know what was going on with them. So we didn't really know until a few years ago, when with the HAWC observatory, that is a water Cherenkov detector observatory that works in the very high energy gamma ray range, we detected two very extended sources that are surrounding the pulsars Geminga and pulsar B06, 56 plus 14. These pulsars are older than 100 kiloyears, and basically what we measured was that the emission, the very high energy emission that we are measuring between 8 and 40 TeV, is produced by electrons that are being injected by the central pulsars and inverse Compton scatter the CMB that is everywhere, and produce this very high energy gamma ray emission. But this was not only the most important thing that we were measuring, but when we measured the profile of the emission of the very high energy gamma ray emission, we realized that well, the only possible transport mechanism transporting this very high energy electron was diffusion, and over there you have the best fit profiles for the diffusion coefficients that we derived from these sources, and we found that the diffusion coefficient is actually 2 orders of magnitude than the average that has always been considered for the propagation of cosmic rays within the galaxy. And this has very profound consequences that I will describe in the following. But before, in order to let you know what is really the size of the regions that I'm describing at the moment, I'm going to put you a video in which you can see over here. You have the X-ray and infrared picture of Geminga, and you can see over there we have 1 arc minute. So over here we are really seeing the Pulsar nebula, this very weak synchrotron nebula that is generated by these electrons and positrons that are injected by the pulsar. Over here you have an illustration of what could be what we are seeing in X-rays. And over here you have basically the same as before, but also with an optical image. And now this image is going to go back, and you are going to see that actually what we see in X-rays is extremely small compared to what we see in very high energy gamma rays. It is several orders of magnitude smaller than the X-ray emission. You can see over here that I have marked over there 1 degree. You can see that we see some huge things. If you look at the Gemini constellation one night, you already know that this is something that is really huge. And because if it was really big, we wanted to understand whether really the energetics in the region was somehow dominated by the pulsar, or it was dominated by something else. And that is why over here you have the over here you have the slide in which I will not make everything to scale, but I hope that I can transmit the knowledge of this region. So basically we have Geminga, we have the Earth 250 parsec. It is actually not very far away. And everywhere we have the interstellar medium. In the interstellar medium, due to the energy density of CMB, other photon fields, magnetic field, cosmic rays, and so on, we have something of the order of 2-3 electron volts per cubic centimeter. So if you calculate the energetics in Geminga, actually the only region where Geminga dominates over the interstellar medium is where we see this synchrotron, very small nebula of the order of less than 0.1 parsec. But what happens in this very big region that we actually see in a very high energy gamma rays? So what we actually see is something that is of a radius of around 25 parsecs, and that is in which the energetics is 4 orders of magnitude smaller than that of the interstellar medium. So with this argument, you can realize that what we are seeing, are not electrons that are are not electrons that are confined into the Pulsar nebula, but these are electrons that are freely propagating into the interstellar medium. It was the first time that we measured the escape and the efficient injection by these sources of electrons into the interstellar medium. And that is why the source cannot be called anymore a Pulsar nebula, because it is not dominated by the pulsar. It is not dominated by the pressure of the interstellar medium energetically. So what we see here are what are now called TeV halos, or simply gamma ray halos around pulsars. Or there are still we're still discussing about the nomenclature, but it is basically a new type of source in which electrons are efficiently injected into the interstellar medium and simply diffusing away without being dominated by a central source, and inverse Compton scattering the ambient photon fields and glowing in very high energy gamma rays. But actually, not only very high energy gamma rays. Well, over there you have the paper in which we put forward this new description that came from the other paper that we published with HAWC a few years ago. But it was not only, so these sources are not only glowing in very high energy gamma rays, but also in lower energy gamma rays. Fermi found that that there is emission from these kind of sources, and actually from Geminga over there you have the reference to this article. These people measure that they measure that the diffusion coefficient, that is the most important thing, because we are saying that it is actually 2 orders of magnitude smaller than that of the interstellar medium. They measure that we got it right, and they are simply seeing something that is slightly larger, because at lower energies, well, electrons cool in longer times. So that was also very important for the confirmation of the measurement we had performed. But there are also other new candidates for sources that that could be of this nature. We're still working on them, and well, basically at the moment there are still only 2 confirmed sources, but not only by wide field of view experiments like HAWC and Fermi, but also recently, a couple of years ago, the measurement was confirmed by an Imaging Atmospheric Cherenkov Telescope, and it already measured, the HAWC collaboration already reported that they had discovered extended emission around Geminga, and they measure a diffusion coefficient that is also compatible with the one we had put forward. And with all this, what I want to transmit is that in the future, with the Cherenkov telescope array that will have wider field of view cameras, we will be very competitive, into the current characterization of these kind of sources that are so important in order to study cosmic ray acceleration and escape in the galaxy. So, sorry. So I've already told you that these sources are accelerating electrons, they are escaping, they are propagating in a diffusive way into the interstellar medium. And at the beginning of the talk, I already told you that we wanted to know what was the origin of the positrons that we were measuring locally here at the Earth. So the next question is, well, how far are these electrons traveling? So are they really reaching the Earth, or they cannot be contributing significantly to what we measure? So with that, I wanted to put you another quick video in which you will see, well, a sketch of what is really the situation between these sources and here at the Earth. And here now everything will be put to scale. That will be also more helpful for you to understand what is really the scale of the measurement that we are measuring, that it is actually pretty huge, something larger than 5 degrees, as I already told you. So over here you have Geminga and the other pulsar, and you can clearly see that everything here is made to scale, as I told you before. And basically what we are seeing in very high energy gamma rays is the blue circle that has a radius of 25 parsecs, and we are only 250 parsecs away from the Earth. So you may think, okay, if these electrons are escaping from there, the lower energy ones, they may be reaching the Earth. But actually, due to this very slow diffusion coefficient, even the lower energy ones, they are not really reaching the Earth. And you can see that better here. When you go to lower energies, to energies up to down to 1 TeV, you get a peak. The size of the region is still cooling dominated, and then for smaller energies, the size of the region is H dominated. And basically here, what you can see is that the diffusion radius of for the propagation of these electrons is actually not reaching the Earth. In order to calculate the full contribution, this diffusion radius is simply an average. So you need to solve the full diffusion loss equation to take into account also the very high energy gamma ray emission and so on. And for that, we wrote this library that is actually open source. You can find it on GitHub and use it as you like. And we basically studied every single of the parameters that are affecting the diffusion of these electrons and positrons to the Earth. And with that, we published this paper, and we were able to claim in the paper we published in the Science Journal that none of these two sources can contribute significantly to the electron and positron flux here at the Earth if the diffusion coefficient, if the propagation of these electrons and positrons continues with the diffusion coefficient that we have measured from the source up to the Earth. They would be simply not reaching us in order to contribute significantly to the measurements we are performing here using satellites, using cosmic ray satellites. So, well, the next question is, well, you have told me that you have measured a diffusion coefficient, but this diffusion coefficient that you have measured, it may not be the same one from the sources up to the Earth. And well, there have been some papers saying that you can assume a two-zone diffusion coefficient in which there is a source, and then there is something outside the source in which the diffusion coefficient comes back to the value that we use in average for the galaxy. Well, this is actually, as I said, this is a proposal, but there are several reasons to think that actually Geminga and the region around Geminga is not especially different from any other region, actually in the galaxy, or at least locally. Well, we already know that well, already there was a supernova explosion, but that was 300 kiloyears ago. The pulsar proper motion is actually pretty high, so it has escaped from the region where the supernova exploded, so it is not affected by the supernova random. Then I already told you by the energetics reasoning that the pulsar is not modifying whatsoever. It doesn't have power enough in order to modify the conditions of this whole region. And actually, Geminga could be inside the local bubble, and over there, the region could be that in that region, the conditions are different from the rest, from the conditions in the rest of the galaxy. And well, so it doesn't. So the diffusion coefficient does not need to be the average one we use in the interstellar medium, but actually the average one we derive for the interstellar medium does not even need to be the correct one. It is only the one that is giving us the best fits as making some assumptions. But actually, it could as well be that it is not exactly that one. But well, as I told you, over there you have some papers in which they perform different assumptions. Well, a bars-like emission plus a two-zone model. People assume convection plus diffusion, but this doesn't work because the convection cannot be powered by anything, by the energetics in the region. And basically, well, over there you have all the reasonings, and also, the very important thing is that we have confirmed with Fermi that the slow diffusion region extends for a larger region, and then it doesn't make any sense to consider that something is inside the source or something is outside, because the only thing that is limiting the inside from the outside is the limits of our measurements, because we will be measuring in a given energy range up to which the electrons will be reaching because of the energy range in which our detector will be will be measuring. So now, if these two sources are not significant contributions, would there be any way in which we could boost their contribution to the electron and positron flux here at the Earth for them to be significant contributors? Well, we studied that. For example, there was a paper in which people were proposing that there could be here in the Earth, here nearby the Earth, there could be some strings of cosmic rays that would be very efficiently transporting the cosmic rays from sources up to the Earth. It would be complicated that in principle these streams should be parallel to the spiral arms, and the direction from Geminga to the Earth is actually perpendicular from the spiral arms. But nevertheless, we considered this as an option, and we studied it by assuming different correlation lengths for the propagation of the electrons and positrons from Geminga and this other pulsar. And in principle, if you want to have efficient propagation from Geminga up to the Earth, then you need strings of cosmic rays with correlation lengths of the order of 100 parsecs or so, because otherwise they wouldn't be reaching us in a very efficient way. So what we studied was whether the symmetry in Geminga was compatible with these strings of cosmic rays. And we simulated different correlation lengths for the propagation of the cosmic ray electrons that are producing the very high energy gamma ray emission. And over here you have an example of simulated correlation lengths of 40 parsec. Remember that in order for them to reach efficiently the Earth, they would need more than 100 parsec, but we already saw that that reaching 40 parsec was already enough, because it is actually not reproducing the morphology that we see from the source. We realized we performed different realizations of all these. We performed some statistical analysis, and we found that first of all, the most likely magnetic field was something between 3 and 4 microgauss in the region, and the best correlation length for the magnetic field that was best reproducing the data that we had measured with HAWC was 1 parsec. So with a correlation length of 1 parsec, we get the best fit to the surface brightness profile that you can see over there on the right. And then this is of course not making possible that there are these strings of cosmic rays from the sources up to the Earth in order to efficiently propagate these cosmic ray electrons and positrons. So I'm giving several no answers, let's say. Well, if these sources are not the main contributors of these positrons here that we measure here at the Earth, so could there be other pulsars that could be the main contributors? And well, over here in this plot, what I showed you is basically all the pulsars that we have within 500 parsec. And well, if we get rid of the old ones, because the very old ones, in principle, they are not producing too many electrons because of their power. Basically, we end up with only these ones that are slightly more than 10. And if you plot over there the sensitivity of the HAWC observatory in order to detect them, well, you basically see that the HAWC observatory has seen practically all the pulsars that are nearby, and that should be producing these very extended halos. And well, you have one over there that is at the limit of the sensitivity at too high zenith angle, and also has a spin down power that is smaller, so that is probably the reason why we didn't detect it. But basically we see the other two ones, so Geminga and Pulsar J0659 or B0656. But there are several other pulsars over there that could be producing a significant emission. So what we are proposing is to build also a wide field of view experiment in the Southern Hemisphere in order to be able to test whether these pulsars are producing a significant emission at these energies. So basically, over there you have a contribution that I'll be presenting next week in the International Cosmic Ray Conference. There is the idea of building this wide field of view experiment in the Southern Hemisphere that will basically, well, depending on the latitude at which it will be located, will basically be able to see all the pulsars that are interesting for us in order to detect these TeV halos and characterize them. And well, with this wide field of view observatory in the Southern Hemisphere, actually, there are several ideas that have been put forward in order to build it. Some people have said, actually, we published a paper a few years ago in which we propose a wide field of view Imaging Atmospheric Cherenkov Telescope called Machete. And well, it had some advantages and some disadvantages with respect to experiments like HAWC that use only water. They operate all the time. They have well, basically have a larger duty cycle, but angular and energy resolution is not so good. But basically, with this, there was a collaboration form called SWIGO that started in a couple of years ago, and in principle, right now we are working on the development of this observatory that will be located in the Southern Hemisphere, and all these people, all these countries with several institutions and so on are already involved. And basically, we will be expecting to start the building of the observatory in well, in principle in 1 year, but with all the COVID pandemic and so on, probably everything will be at least delayed for 1 year or so. But in principle, with this, we will be able to characterize all these sources and that will be in principle surrounding all these pulsars in the Southern Hemisphere, and we will be able to detect several more, because in the Southern Hemisphere we see a larger part of the galaxy. And well, so I have already talked to you about again about several have already given you several no answers. Also, these sources are not explaining the cosmic ray flux we measure here at the Earth, or the electron and positron cosmic ray flux here at the Earth, especially if we assume that the diffusion coefficient is the same one between the source and here to the Earth. So if none of the known pulsars can explain this cosmic ray flux that we measure here at the Earth, can pulsars still explain not only the the positron flux and the positron excess that we measure here at the Earth, but also very important is what is called the all-electron flux. So the all-electron is called like that because, well, basically, for example, experiments like Imaging Atmospheric Cherenkov Telescopes cannot distinguish between electrons and positrons. So you measure the all electrons, you measure electron and positron flux. And actually, this electron and positron flux has been measured up to energies up to 20 TeV. 20 TeV is a lot, taking into account that these electrons and positrons, they cool down, they lose their energy pretty fast because of synchrotron and inverse quantum cooling. So basically, if you assume that the diffusion coefficient for the propagation of these 20 TeV electrons is the same one that we measure with HAWC, it would mean that on average, the diffusion coefficient would be something around 25%. And this is nearer than any known pulsar. So this, of course, 25, again, is the diffusion radius. You need to solve the full diffusion loss equation. but you can go a few times more than farther than this, but we do not have any pulsar that can actually explain this. So what we started to think was, well, pulsars, or known pulsars at least, they have their beams pointing towards the Earth, and that is why they are called pulsars. But what is the beam fraction that actually points towards the Earth? And we figured out that this is actually less than 30%. So more than 70% of the pulsars that are out there, they can be detected as steady sources, as X-ray steady sources, even as gamma ray steady sources. And we would simply not be seeing the pulsation because the beam is not pointing towards us. So there can be pulsars out there nearby that we do not know that they are pulsars. So we perform a theoretical study, and we try to evaluate, first of all, whether there could be a pulsar that would be explaining the all-electron flux that we measure here at the Earth, together with the slow diffusion coefficient that we measure with HAWC. And well, this theoretical study, we started, first of all, we started to consider whether there was one pulsar or more pulsars that could be explaining this all-electron spectrum that we measure here at the Earth. And here in this plot, what you have in the three different colors are three different diffusion coefficients. And the one that we measure in Geminga is roughly the blue one, and the average in the galaxy is roughly the yellow one. And here, 100% means that at that energy, there is only one contributor. So we perform simulations of distributions of the pulsars in the galaxy. And if we assume that we have a very slow diffusion coefficient, the probability that electrons and positrons above 1 TeV are only coming from one pulsar is practically 1. So it would mean that the all-electron spectrum between 1 and 20 TeV would need to be reproduced by only one pulsar. So then we tried to derive the properties of that pulsar, and actually the properties of that pulsar, leaving as free parameters some of the things that we cannot measure on the pulsars. So actually over here in this plot, you have the all-electron spectrum that a pulsar at 50 parsec and with the characteristics over there that you can see an age larger than 300 kiloyears, distance between 80 and 90 parsecs, and spin down power pretty reasonable between 10 to the 33 and 10 to the 34 X would be producing. And we left everything as a function of, for example, the birth period of the pulsar, because the birth period of the pulsar, we have absolutely no idea about it. So if the birth period was larger, then it would be well. If it was larger, then it would be emitting less emission now. If it was a smaller birth period, then at the beginning of its life, it could have produced more emission, and so on. So basically, we derived the characteristics of a single pulsar, a single unknown, undiscovered yet pulsar that could be explaining not only the positron flux at the Earth, but also the all-electron spectrum we measure between 1 and 20 TeV. And you can see here, before I was showing you the all-electron spectrum, you can see here also the positron excess, also the anisotropy that we do not violate with the contribution from this pulsar, and so on. And well, so basically that was our paper, and the bonus track was actually something pretty nice, and it was that just a little bit before we published our paper, there was another paper in which they were modeling let's say the supernovae that carved the local bubble based on the measurements of the iron 60 measurements here at the Earth, and modeling its transport. And these people published their paper in Nature, as I said, a few years ago. They actually found that, well, the local bubble had been carved by something like 15 or 16 supernovae, but the two most recent supernovae had exploded at a distance of around 90 and 100 parsecs and 1.5 to 2.3 mega years ago. And that was pretty compatible with the pulsar that we were proposing. So that was pretty nice. Now it would be complicated to discover this pulsar, but we have been investing some time into trying to find it, because it would be awesome if we do. So finally, I'm already finalizing. I just wanted to say that the gamma ray future is very bright for the detection of these kind of sources and the study of particle propagation and acceleration in this kind of sources, this TeV Halos, that is a new type of source. There is an observatory that has just started operation in China. They are actually, next week, they will be releasing their first results. They have already published a couple of papers, the very good ones that are already changing how we understand well, not only this kind of sources, but also other kind of sources at very high energy gamma rays. The SWIGO collaboration, I already told you, that has already started. It is actually advancing, and we are pretty confident on building an observatory in the Southern Hemisphere. And the Cherenkov Telescope array is currently being built and will also play a crucial role in the understanding of all these kind of sources. Now, just to finalize everything that well, I've presented here, we already organized a workshop on gamma ray halos to try to give some definition to them. There were many participants and there were a lot of followers from the community. Over there you have all the talks, all the presentations, the slides, and so on, in case you are curious about it. Well, at the moment we are writing a review that should be published well, hopefully soon. And yeah, and also sorry for the biased view, because of course I am presenting here in this talk more my results than the ones of others. But yeah, so if you are more interested about these kind of sources, please go over there, because you can find everything. So I'm finalizing, and let me go to my summary. So basically, what you can get from this talk is that HAWC has measured the extended emission surrounding two middle-aged pulsars that is produced by electrons that are diffusing away from the sources and inverse quantum scattering CMB. So this the best fit to this morphology that we have measured is that only diffusion is the one explaining all this propagation. And also due to the energetics of the region, we know that the electrons and positrons are actually escaping from these sources. The diffusion coefficient we measure for these escaping electrons is actually 2 orders of magnitude smaller than the one that is assumed as an average in the galaxy, and this can have profound implications for the propagation of cosmic rays, not only nearby the Earth, but maybe also within the whole galaxy. And well, I have already shown here that the main contributor for the positron flux at the Earth cannot be any of these two pulsars if we assume the same diffusion coefficient from the pulsars up to the Earth, and different pulsars and diffusion parameter assumptions, and also asymmetric diffusion and so on. They do not change the conclusions over here. And finally, for the explanation of the cosmic ray flux we measure here at the Earth, we propose that an undiscovered pulsar inside the local bubble could be the answer for the answer reconciling the diffusion coefficient we have measured in Geminga and the cosmic ray all-electron flux we measure here at the Earth. And that's it. Thank you.
Thank you very much, Rubén, for this very nice talk. And now the talk is open for questions. Please, for all participants, raise your hand, and Ivan, which is the person working in the same group as Rubén, will manage all the questions. So please, Ivan, the floor is yours. And do questions to Rubén.
Yes, first of all, thank you very much for the super nice talk, Rubén. That was very enjoyable. Okay, so we have a few minutes for questions. So is there anyone who wants to start? Yeah, Miguel, please, you can go ahead.
Oh, hi, Rubén. Thank you very much for the talk. A lot of stuff, very useful information, Rubén. So congratulations for these achievements. I'm one of the. Unfortunately, I couldn't join earlier, so I'm sure I missed a number of important things. But anyway, one thing that struck me a lot was this incredible image where you showed Gemini. I mean, this constellation, and you had this extremely large area with emitting in. I think it was, well, not the movie actually. So I think it's better if you show the slide where you have the Gemini constellation and there is a zoom into the region where there is a lot of CTA. I guess it's CTA, right? Or magic detection.
I think it was
in the movie, maybe. Well, anyway, the point is, what is then the origin for such a large scale, as in gamma ray emission? Is this more or less clear? I didn't get the message in this.
Yes, yeah. So I think it was a movie. Let's see if it finishes and. So let's see a moment. Is it this one, Miguel?
Yes, this one. Yes. So when you show, okay, yeah. So it was part of the movie.
It will appear now. The emission. Yeah. So with the movie, what I was trying actually to illustrate is that actually you can see over there so at the beginning of the movie you can damn it. Okay, sorry. So at the beginning of the movie you can actually see that here you have the synchrotron emission. That those are electrons and positrons that they have a magnetic field that is smaller than 10 microgauss and are producing here the X-ray synchrotron emission. And the same electrons and positrons that are producing this synchrotron emission, but that are escaping from the source, are the one producing a much larger nebula or halo, a much larger halo by inverse Compton scattering CMB. So, but actually the point is that these electrons and positrons are escaping from the source and they are simply diffusing away. That is why the 1/r profile.
So have you found more of these sources in the sky? Is this what is, or maybe what is peculiar about this region to have this there and not maybe in other parts?
So the problem is that it is difficult to detect these kind of regions. First of all, the pulsars are very weak. This here we are talking about 10 to the 34 ergs per second, and the regular sources we detect in very high energy gamma rays are about 10 to the 36. So you need them to be very nearby. But if they are very nearby, then they are very large. And if they are very large, with imaging atmospheric Cherenkov telescopes, it is difficult to detect them because you have a camera that has a field of view of 3, 4, 5 degrees. And here what we are seeing is something that has a 5.5 degree radius. So that is the reason why it's been so difficult to detect them so far.
Okay, thanks. Okay, so it is actually then a large in terms of angular scale. Intrinsically, we can expect that any pulsar would make such a region, but just if they are very far, then we don't detect them.
If they are old enough, because otherwise electrons and positrons may not be escaping so efficiently. Here, they are. So here, 40% of the spin down power of the pulsar is being injected into the electrons that are escaping. So it is really a lot. It's
okay. Yeah, thank you very much.
Thanks.
Okay, thank you very much, Miguel. There is another question by Anchoni.
Yeah, hi, Rubén. It was a very nice talk. I am very curious about this undiscovered pulsar inside the local bubble that is able to explain the position excess, the positron excess and the all electron spectrum. Is really amazing, no? That is able to explain that. And also you mentioned that you have this result coming from the iron. Is that correct? I mean, from
that wasn't my result. It was
from the literature. That the properties of this source are very similar to the ones you need in order to explain the positron excess and also the all electron spectrum.
Yes.
Yeah. Which is the next step in that sense? I mean, it's because it's a very strong prediction, really.
Yes, but it is very complicated to to try to measure. I mean, if the beam is not pointing towards us, then there could be some. I don't remember. So there were some in the paper we discussed about some X-ray measurement of the Magnificent Seven or something like this. They are calling them, that are in principle they are isolated neutron stars for which you only measure the surface temperature in X-ray. Yeah, actually. So how do you measure them in X-rays? But then it is complicated to pinpoint one of those to be a pulsar and also to be at the right distance and so on. So we try to search in, for example, in Fermi for all the nearby and unidentified sources and so on. We made a list. We also tried to search in X-rays. And we thought on putting out some proposals, but from our side, for example, it is complicated because everything is isotropic. But from the side of the iron 6, they are actually pointing towards an LB region, and this is where we focus most of our searches. But unfortunately, after the publication of this undiscovered pulsar paper, we haven't found anything worth publishing. So if you have suggestions, that would be awesome.
I would like. No, but it's very impressive. Then, I mean, this single pulsar would be able to explain the whole the whole positron excess, really.
Not the whole positron excess, but it is important that it doesn't explain the whole positron excess. Okay. And just let me explain why. So in the first slide about this how many pulsars that I showed you, I told you that above 1 TeV there is only one pulsar contributing, but below 1 TeV there should be more pulsars contributing. There is not, we don't reach this 100%, and therefore if only with one source you are able to explain the positron excess at 100 GeV, then you are doing something wrong, because there are more pulsars that will be contributing there. Okay. So the contribution from this pulsar should be one of the ones that are below here, because otherwise the contribution from other pulsars will not be taken into account, and we will be overshooting what we are actually measuring here. What we reproduce with all the solutions, what we have to reproduce is the all electron spectrum between 1 and 20 TeV. Because if we assume the diffusion coefficient we have measured, there can only be one pulsar contributing between 1 and 20 TeV. And it should be this one.
Okay, thanks a lot for the explanation.
So I don't see any other question or raised hand right now, but I actually have one question, perhaps two. I'm going to try to be, because we are short in time now. First of all, I missed for the very high energy gamma ray emission from the Geminga complex that you showed at the beginning, I understood that you were interpreting that emission as inverse quantum of relativistic electrons from upscattering CMB photons. But I missed the argument why that is the preferred model of for the emission. Did you explain it or?
I don't know if well, probably I didn't clarify it enough. So there have to be electrons inverse quantum scattering CMB. Well, first of all, because at these energies, if you have, well, synchrotron is absolutely impossible. Bremsstrahlung you wouldn't have energy enough in order to explain this. And then inverse quantum scattering only CMB. It is because, well, we also in the calculations we also include infrared, optical, and so on. But these energies are so high that you are already very deep in the Klein-Mishina regime. So it means that for the photons that are produced by electrons, inverse quantum scattering, for example, infrared or optical, you would need to have energy densities of infrared and optical that would be too high and that are actually not seen in the region. So that is why the emission, in principle, the main contribution to this emission by far is that of inverse quantum scattering CMB.
But when you say that synchrotron is impossible because of the high energies, you mean synchrotron from electrons? Wouldn't be possible synchrotron from, proton synchrotron?
But that wouldn't be efficient enough, and you would need to be you would really need to be getting the protons from somewhere. Over there, the only thing you have is a pulsar. In principle, even if you assume that all the energy of the pulsar is injected into protons, you wouldn't be able to explain that, because you will need need a lot of protons. Synchrotron emission by protons is much less.
Yeah. Okay, that was the piece of information that I was missing, just because of my ignorance in the field. Okay, the second question was very shortly. It's nice to have predictions from supposed sources in the surroundings, like the pulsar that you were mentioning. But actually, at some point, to confirm that hypothesis, you have to show that there is that pulsar. So, are there any ideas? Because actually, this is not a problem in this field, but there are many other people trying to hunt for missing pulsars everywhere, especially also in the galactic center. So, are there any ideas about how to catch them, how to hunt for them?
So, for example, from our side, for this kind of source, I told you we tried to search for it in X-rays, R-rays, gamma rays, and so on. For example, in Fermi, even if the beam is not pointing towards us, what people have been doing is to use machine learning techniques in order to compare what is the spectrum that is produced by a source. Because, well, when you work in Fermi, but you've worked with Fermi data, so you probably know that if you look at a spectrum, and sometimes you say this is an identified source, and you look at it and you say this is a pulsar, but we just don't see the pulsation. What people have been doing is to use machine learning techniques in order to try to derive that. You assign a probability of a source to be of a pulsar origin based on other sources that you have seen the spectra, and they are pulsars. But with that you assign a probability, and then it is difficult to assign, for example, a distance. So you can only say that it is at a location in the sky, and if you don't have any other information, then it is very complicated. So this is so to univocally identify them is very complicated if you do not see the pulsation.
Okay, all right. Thank you very much. I think René, we can stop here. No.
Yeah. Thank you very much, Rubén, for this talk. Thank you for all the participants. And
Thanks a lot, Rubén.
Sorry?
Thanks a lot.
Thank you.
Yeah. And see you next week for the next talk. Thank you very much.
Okay, thank you.